Yes.
Yeah,
Okay, it's recording.
Yeah, you guys can see my screen share?
Yes.
Yes.
Okay, very good. Okay, so, I'm reporting on some joint work with Dmitry Gurevich at Weizmann and Raul Gomez is at UANL Mexico. And this work has to do with the Stone-von Neumann equivalence of categories for smooth representations of the Heisenberg group. We were sort of led to this in this sort of a natural question in the course of our studying Whittaker functionals. And I probably won't have too much of a chance to explain that, but if you look at the paper, we indicate one connection, but that's not sort of the only connection. We're hoping for more, but anyway, these are just developing some tools that might be useful in the study of Whittaker functionals, and then by extension to representations and automorphic forms. Okay, but the result is, but people care about the Heisenberg group for many reasons, so it's kind of good to have something about the Heisenberg group, right? The Heisenberg group or the Heisenberg-Lie algebra is like so important. So anything you can prove about it might be applied in ways you didn't have in mind to begin with. Okay, so let me just recall first the Stone-von Neumann theorem, which we are looking to generalize or promote to an equivalence of categories. So the Heisenberg group, it's an extension of a symplectic vector space by a one-dimensional center. So I will call W for the symplectic vector space and Z for the one-dimensional center. Extension via the symplectic form. And it plays an important role in many areas of math and physics. And the fundamental result, which is due to Stone and von Neumann, relates the characters of Z to representations of H. So more precisely, let chi be some non-trivial unitary character of Z. And the theorem is that there's an irreducible unitary representation rho equals rho chi of H, unique up to unitary equivalence, in which Z acts by this character that you prescribed. And this result plays a central role in, for example, I sort of, yeah, I was exposed to this as a grad student by Roger Howe, and so it plays a central role in the construction of the oscillator representation of the metaplectic group, which is a double cover of the symplectic group SPW. And an important application of this is this theta correspondence for automorphic forms and so on. That is what sort of I understood from Roger Howe. But it also there's a local theta correspondence, which is important for representation theory of real groups. And there's a global one, which was the original motivation for this. Okay. So that's the basic theorem. Any questions about this? No, it's all should be pretty clear, right? Okay. Let's explain the generalization. So what I'm going to describe is generalization of this result to an equivalence of categories between suitable categories of representations of H and of Z, rather than just irreducible, non-trivial irreducible goes to non. So rather than just a unitary correspondence, we're going to get some smooth version of this result. That's the goal. Sorry, we want to get some non-irreducible version. So in fact, there are two. So the first is some algebraic version of the story. And this I'm going to explain in the first result, theorem A. And after we did it, we realized that it was very closely related to something that's called Kashiwara's lemma in the theory of D modules. And the reason it's related is because the Heisenberg group is closely related to the Weil algebra. So this is why it kind of, when you do something here, then it has some also some interpretation. I mean, this is one of the nice things about the Heisenberg group. So it also connects to D modules, and this algebraic version is useful for that. And I don't know if this may sort of be known independently, but anyway, let me state it to set the stage for our more meaty result, which is the analytic result. Okay, so the second generalization is it's given in theorem B that I will explain, and it involves what we call non-singular representations of Z and H, which take some defining. Smooth non-singular representations of Z, and it's a much more delicate thing. It involves quite a bit of functional analysis and topological vector spaces and operator theory and the like. And it involves fundamental ideas of Foucault-Duclos. So this is Foucault-Duclos before he worked on Atlas. He has a big paper on differentiable representations and smooth imprimitivity systems for Nash groups. Yeah, Foucault is amazing. He can do all sorts of things. So, but that's involved in here. And a key new idea, so it's ideas of Foucault-Duclos, and a key new idea is the construction of something that we call the big oscillator representation, capital omega. And this big oscillator also extends to the metaplectic. So first, it's a big oscillator representation as a representation of H, and then it also extends to the metaplectic double cover MP of the symplectic group, and this is theorem C, that the thing extends. So this omega is used in theorem B, but then we show that it extends to the metaplectic group, so that's theorem C. And then this allows us to extend theorem B, which was some matching between representations of H and representations of Z, to module categories for MP semi-direct product H and SP semi-direct product Z. And this MP semi-direct product H is sometimes called the Fourier-Jacobi group. And so then you have an equivalence of categories here. So it's a promotion of theorem B. Using theorem C, we promote theorem B to theorem D. Okay, there's also theorems E and F, but I'm not going to talk about them. This is kind of enough. That's already quite a bit. You can, after you read this, then you can see what's happening in theorems E and F. Then they get into Whittaker functions and the applications. Okay. All right, so let me first explain the algebraic result. We don't need it for the second part, but it kind of sets the stage, and it's kind of cute anyway. So, okay, so let L be a maximally isotropic subspace, or a Lagrangian in W. Then L and P equals L times Z are abelian subgroups of H. Okay, I'm going to, L times Z I'm going to call P. So LZP, they're abelian subgroups. And we write in the usual Gothic, in the Fraktur notation for the Lie algebras and the usual notation for enveloping algebras. Okay. Now we choose a generator Z for the one-dimensional Lie algebra script Z. And we write M of Z cross for the category of Z modules on which this little z acts invertibly. That's the non-singular Z modules. Just algebraic Z modules in which little z acts invertibly. So evidently this category doesn't really depend on the choice of little z because, they're just related by scalars. But you want something in there to act invertibly in the module. So the algebraic result concerns the category which I call M sub L of H cross, which consists of H modules. So H is, remember, the Heisenberg right here in this notation, satisfying the following two conditions. First, L acts locally nilpotently, and Z acts invertibly. In other words, the restriction of this module to Z is in MZ cross. But also it's locally nilpotent for L. L action is locally nilpotent. So there's two categories, MZ cross and MLH cross. Okay, so now if I have an H module, I let M upper L denote the subspace of L invariance. And this is a Z module. The ML invariance, that's a Z module. And the first theorem is that this functor M goes to L invariance. It's an equivalence of categories from MLH cross to MZ cross. Okay. That's the first theorem, the algebraic theorem. Any questions? I feel like yeah, I hope I'm not going too slow or too fast or something. Jim, you know that feeling from teaching Math 350. So please say something reassuring. That's good, okay, fine. I don't want to go too far. Somehow you should complain about something.
No, it's good. It's good.
It's good. Okay. Shifi, it's okay, right?
Yes, I'm fine.
Okay, good.
I think I forgot what was L.
M.
L.
Oh, L. L was a Lagrangian.
Okay.
So here. So the Heisenberg group is made from a symplectic vector space W.
Yes.
And the center Z. And L is some maximally isotropic subspace. L is short for Lagrangian.
Okay, thanks.
And P is L times Z. And H is the whole thing. Okay. So, and the modules are supposed to have, L has to act locally nilpotently, which means, yeah.
So the theorem A is only about the Lie algebra, right?
Yes, it's algebraic theorem.
Mm-hmm.
That's what I mean. It's an algebraic theorem.
Mm-hmm.
Right? Yeah. Yeah, it's all Lie algebras. Okay, and so how do we prove that this is an equivalence of categories? So we construct a quasi-inverse. And the quasi-inverse is just this extension. It's an induction. So so what you do is you extend N trivially from a Z module to a P module, and then you just do induction. And okay, then you have to prove, so you have a functor, you have functors in both directions, and you have to prove that they're quasi-inverses. And what is involved in here is the following lemma. That suppose you have a module for the Heisenberg, three-dimensional Heisenberg. It's enough to do it for the three-dimensional. The main ideas are here already. I mean, the theorem is for any Heisenberg, but the key idea for the three-dimensional case is that you have a Heisenberg Lie algebra and you choose x, y, z, satisfying the usual relations. Then the kernel of x to the j plus 1 is obtained by applying y several times to the kernel of x. So it's a sum. This is some key factor of the Heisenberg, and that's what's needed to prove that the two functors are quasi-inverses. Something
So in vertex operator algebra theory, one has the z-graded, extension of this.
Exactly. Is that right?
And
so this theorem is kind of well known.
Oh, yeah, right. And the theme is just very pervasive everywhere. But
yes.
it's interesting that the z integers graded version of this, where you have to take care of highest weight directions and stuff.
Okay.
It's extremely fundamental also.
Oh, okay. Maybe we can, I mean, I would love to understand this a little bit. Maybe we'll talk at some point. Yeah, I don't know if the smooth version has anything to say for this. I don't know if our smooth version has anything to say for.
Actually, when Robert Wilson and I were writing down what I just said,
yeah,
which wasn't hard, it was just in the air and we needed it precisely. It
okay.
was Nolan Wallach who said, you guys are just rediscovering the Stone-von Neumann theorem, which I sort of knew.
Oh, but the Stone-von Neumann is for unitary. So, but there's no.
Yeah, I know, but for this algebraic.
Yeah, algebraic.
What you're doing now, but for the z-graded infinite dimensional.
So, okay, so at the very least, we should, if you point out the reference, so we will include the reference in this paper.
Oh, no, it's nothing. I mean, my book with Frankel and Merman has it.
Okay. So
I could tell you later. I didn't mean that it's important, but
for us,
what is important is it's such an important theme in vertex operator algebra theory also.
Oh, good. Okay, so then it's kind of doubly appropriate for this seminar.
So Abid has a question in chat.
Yes, Abid. Oh, Abid, you're asking a question in chat?
Yeah, because his voice has some noise or something.
Ah, he has some. Oh, maybe you could just turn it on briefly and ask, or it's. Oh, why do we need locally nilpotent action of L?
I'm sorry, I have a lot of background noise, so sorry. I don't want to interrupt. I didn't want to interrupt.
Okay, but when you ask a question, you can just kind of flip it on and off. I think that's not a problem, right? As long as
I can move to next some other place.
Yeah. Right. I mean, it's not true without assuming local nilpotence.
Yeah, my question is about local nilpotent action of this L, the algebra L.
Then it's not true. The theorem is just not true. It's an equivalence. So the category MZ cross is well defined, and it's equivalent to some category of H modules, and it's these categories MLH for any choice of L. They're all equivalent. They're all equivalent to MZ cross.
I see. Thank you.
And what happened? Sorry.
Go ahead.
Oh, that local nilpotence is analogous to the highest, weight type of situation.
Yes.
Grading bounded from above or below, whichever direction you feel like calling the grading.
Right.
And the cross, what's the role of the cross?
Cross just means that you're not allowed. So
I know what it means, but why do we require? I mean, why?
Otherwise, it's false. The Stone-von Neumann theorem is false also. Because if the center acts by 0, then you just have a representation of W, and it's just basically a character of W, and they're not all different.
Okay.
If you just think about the Stone-von Neumann theorem, you have, if Z is acting by 0, then the representation descends to W.
Okay.
And
then you just have an abelian group acting.
Exactly. And so it's just linear functionals, and they are, There's no uniqueness. Somehow, from the point of view of co-adjoint theory, there's lots of there are lots of yeah. So I mean, you kind of have planes. I mean, you have some three-dimensional picture, and maybe z is along the z-axis. Then the co-adjoint orbits look like planes perpendicular to z, parallel to the xy plane, except the xy plane itself, where it's just all points. And they're all symplectic, co-adjoint orbits are all symplectic. So there's a bunch of, so it's kind of, that's the picture. It's like two-dimensional things, each of which meets the z-axis at just one point. But at 0, the whole xy plane is a separate representation. Yeah.
Thanks.
Something funny happens. So the 0 is yeah. Right. Okay. Okay, so all right. So okay, that's theorem A. Right. Okay. Good. All right. So now let me explain the analytic theorem. So there's quite a bit of stuff, and I'm going to kind of go lightly through it. So the point is that the Heisenberg group and these subgroups PLZ, they're what are called Nash groups. So they're groups in the category of Nash manifolds. And one thing what you can do in a Nash manifold, you have, well, in general, if you have some sort of C infinity manifold, you can talk about smooth functions and distributions and compactly supported distributions and the ilk. But Nash manifolds are algebraically enough that you can talk about Schwartz functions. So you can do the theory of Schwartz functions and Schwartz distributions and so on. And Schwartz distributions are kind of nicer in some way because they're Schwartz functions and so on. They're kind of nicer because they because, for example, for something called the Schwartz kernel theorem, and in functional analysis.
So Nash group means that you have the topology is something like tame things.
Yeah. But yeah, by semi-algebraic or something.
Okay.
Yeah. So in other words, you have right. Mm-hmm. But basically, the point is that you can talk about Schwartz functions on a Nash manifold. That's the main point. Because there's a notion of algebraic. The Schwartz function need polynomials. So you just need to have enough you need to have enough polynomial structure so that you can talk about Schwartz functions vanishing fast, the right sort of vanishing at infinity. Okay, so the Heisenberg group is a Nash group, for instance. Okay, so then for a Nash group, you can look at, since the group is already, you can ask for the category of smooth nuclear Frechet representations of G of moderate growth. This is some right category. So nuclear spaces are, and not, so what I understood, I mean, I kind of learned this, done it in grad school, and then in the course of this project and some earlier project. The way to think about nuclear spaces is that they are some analogs of finite dimensional spaces, which are sort of a different direction to go than from Hilbert spaces. So you can think of that Hilbert spaces as somehow some nice generalization of finite dimensional spaces. That's true. But nuclear spaces are another such generalization. And there is Grothendieck proposed this, and it's some extension. And he proved the Schwartz kernel theorem, or the kernel theorem for nuclear spaces. So it's sort of a good thing to look at.
Yeah, I think the nuclear space, at least there's one important property is that you can take the tensor product as a unique sort of tensor product. Otherwise,
exactly.
you have several. So for
Yeah, yeah.
representation theory, tensor product is important. So that,
Absolutely, absolutely. Yeah. So this is why it's right. And bilinear forms you can understand also on nuclear spaces. That's, yeah. Okay. But you also want to have moderate growth. Fresher spaces of moderate growth. So these are some technical things, but this is some right version of finite dimensional in general. Okay. All right, so now let little z be a generator of this Lie algebra as before. Okay, now we want to define the notion of a non-singular representation of z. So this is just about z for the moment. And you say a smooth, okay, something in rep infinity z is non-singular, some rho is non-singular if there is some rho prime. These are representations of the Lie group of the smooth. Right, rep infinity of z. You have two things whose differentials are inverses. Okay, so certainly a group representation is always invertible, but the condition you want is that the differentials should be inverses of each other. So that's the technical notion. So then I'll say that this is a non-singular representation of z.
So here by differential invertible each other. So differential live in which space? So you talk about.
No, the representation is a smooth representation. Therefore, it defines the representation of the Lie algebra.
Oh, okay, I see. Okay.
D rho is just the derived representation of the Lie algebra.
Okay.
So I said differential, I could just say the derived. So the derived Lie algebra modules are inverses of each other in this sense. That's the condition you have to impose. Okay, and now I will write rep infinity z cross for the category of non-singular z representations. That's the category. And I will write rep infinity h cross for the category of h representations whose restriction to z is non-singular. Okay, and Shifi, here I don't need L to define this category. Shifi and Abid, both of you, right, sort of asked the same. Shifi asked what's L, and Abid asked, why do we need L? Okay, so for this, I don't need it in the analytic story. Okay, so those are the two categories. Yeah, and everything inside is smooth nuclear pressure representation of moderate growth. Okay, so now let me define the big oscillator. So first, z hat and z hat is a Nash manifold, z hat cross is a Nash manifold. So I let S be the algebra of Schwarz functions on z hat cross, on the space of non-trivial unitary characters of z. Okay. So then this A is a non-singular Z module, where the action is just the obvious action. So yeah, A as a Z module, it's in rep infinity Z cross. And the action is just, okay, you have a function on characters. How does an element of Z, this Z is not the same as the differential. Okay, this is some arbitrary element of big Z. Sorry, this is just some bad notation here. But anyway, some element of the group Z just acts pointwise by the character, which is the point. Is that clear? You have a function on character, the group element just rescales at each point you just evaluate. You get a rescaled function. Okay, so what is the big oscillator representation? The big oscillator representation is you take, you induce it. Okay, so now I need an L. So, okay, so the big oscillator representation is the induction of this var pi from P to H, where E of pi is the trivial extension of var pi to a module for LZ. And what is this ind? Well, ind is the correct notion of induction for Nash groups. And this is, Duclos defined it and he called it Schwartz induction. So it's the right thing to do for Nash groups. So you take this var pi, let's call this, I don't know, the character module or something. And then you induce it to and you extend it to some P by choosing the Lagrangian, and then you induce it to the group, to the Heisenberg group, to do Schwartz induction to the Heisenberg group. And this will be, so this is the right thing because, for example, it's a nuclear Frechet representation, which is actually non-singular for H. So it belongs to this category. And moreover, so to define it, I used the Lagrangian, but its isomorphism class is independent of the choice of the Lagrangian L. Okay. So it's some object in rep infinity H cross, which up to isomorphism doesn't depend on the choice. So we could probably make it more unique by doing some category theory nonsense, as taking some inverse limit, but never mind that. We'll have some Lagrangian, but the representation is the representation. Up to equivalence, it doesn't depend. So yeah, that's the big oscillator representation. You took this big non-singular representation, some sort of, I should make a point. So I mean, there's a lemma, which is a key lemma, it's kind of not being said here, but the category rep infinity Z cross is actually the same as the category of A modules with the property that AM is equal to M. What are such modules called in algebra, Jim? Module for an algebra, which is such that the action map is surjective.
What's your question again?
If you have an algebra and you have a module, and the property that the action map from A cross M to M is surjective. I mean, if the algebra is unital, then this is no condition at all.
Right. Maybe that's why nothing comes to mind.
Yeah. But if you don't have a unital algebra, such as the algebra of Schwartz functions, the constant function is not Schwartz. Yet the module is such that. Anyway, we call it a smooth module because this Schwartz algebra, the algebra of Schwartz function, acting on this module is like smoothing. And so you can use that, you can say the module is smooth if every vector, it's like the guarding theorem. Right, it's the Schwartz version of Garding's theorem. Okay, so the category rep infinity Z cross is the same as the category of smooth modules for A. But smooth only makes sense in the present context because this is already some algebra of Schwartz functions. So, but there should be some notion set like this for non-unital algebras, but never mind. Okay, anyway, I mean, it's a key thing, but I had enough over here, so I thought I'd just talk it through and not write it down. Okay, so I have this var pi, which is something in rep infinity Z cross, and I have big omega, which is something in rep infinity H cross. And now, the main theorem. So first, some notation. So if I have two nuclear Frechet modules for a Nash group G, we write rho tensor hat rho prime for this completed tensor product that Yuzhi was talking about. And we write rho infinity, rho tensor sub G rho prime for the space of diagonal coinvariance for this tensor product. Okay. So do I have to explain what this? So coinvariance is, you look at things generated by the action of G on the space. And so you look at GV minus V, things of the form GV minus V. And to get coinvariance, you quotient by that. So that on the quotient, G would act trivially. But in the Fréchet situation, we should quotient by the closure. So that's the point. But this is some well-defined construction. This is why nuclear Fréchet spaces are good also, because you can do such things. You can do the invariance and coinvariance. And nuclear things stay nuclear when you take closures, which is also a good thing. Okay. All right, now we define a pair of functors, C and I, C going from rep H, from H to Z, and I going from Z to H. And it's really just the same construction done twice. You tensor over H with omega bar, or you tensor over Z with omega bar. So you either take H coinvariance or Z coinvariance. So when you take H coinvariance, now what you get is a Z module. On the other hand, if you start with the Z module and then you take Z coinvariance, then you get an H module. Yeah, omega bar is the complex conjugate of omega. So, once you have the right thing, the formulas start looking very simple. It's the same thing that you're doing. You either take tensor product over Z or tensor product over H. Okay, and then the theorem B is that these two functors C and T are quasi-inverses, thus these two categories are equivalent. Oh, C and I, not C and T, oops. Okay, typo. Is this typo in the paper also? There was some other typo which I just fixed here because these functors were going between the same categories. Okay, anyway. So is that clear?
The typo is in the paper, by the way.
Thanks.
No problem.
Okay. At some point, this I used to be T and became I and didn't survive. Yes. So I is a kind of induction, and C is coinvariance. So in coinvariance, you go to a smaller thing, but here, even induction is a kind of a coinvariant. I don't know, central coinvariant. Okay. So that's the theorem B. So any questions about this? Okay, so let me explain the theorem C. Oh, there's some repetition here. Okay, so the Heisenberg group is, as I said before, okay, never mind the repetition. It's an extent, so there's a W and there's a Z as before. And so the symplectic group acts on H by automorphisms. Right, and let rho be some irreducible unitary representation of H with non-trivial central character under Z. Then, okay. So by Stone-von Neumann theorem, okay, so the group is acting by automorphisms on H and it's not moving the center. And so every group element gives you Yeah, so you know that for each group element, the twisted version of this module is isomorphic to itself by the Stone-von Neumann, and what that transforms into is the projective representation of the symplectic group. This equivalence, or more precisely, equivalently a representation of the universal cover. And the big theorem of Siegel, Schale, and Way is that this representation, which is a priori a representation of some universal cover, descends to a double cover, which is the metaplectic group. Okay, so this is the Siegel-Schale-Way theorem. And so our theorem C is just a generalization. So it says that there's a unique extension of this omega, the big oscillator, to a representation of this semi-direct product, MP semi-direct product H. So that's true. I mean, that's the Siegel-Schale-Way theorem is for the little oscillator corresponding to an irreducible guy. And this is the smooth version of that for the big oscillator. And what's amazing is that the big oscillator is very big, yet you can prove things locally. So point by point. It's just kind of put together just right. There's a unique extension. Okay. All right, so now let me explain theorem D. Okay, so I look at the category of non-singular representations of MP tensor H. So these are just representations. MP tensor semi-direct product H is a Nash group. Everything is Nash. And so those are the representations whose restriction to H is a smooth representation of H. And okay, fine. I mean, it's the same as the restriction to Z is a smooth representation of Z, a non-singular representation of Z, because that's how I was defining. So it all comes down to Z. But I want to write rep infinity minus, so this minus sign is the subcategory of genuine representations. So genuine means representations. So this is a representation of MP, which is double cover, and genuine means that it does not descend to SP. Okay. Yes. Yeah, probably. Okay. Yeah. Okay. So this is a subcategory of genuine representations. All right. Okay, now I can define, yeah, okay, I just realized that probably one needs to be, since we're talking about non-irreducible representations, I need to formulate the notion of genuineness a little bit better. Okay. Anyway, I don't have to go into it right now. Just realize something, probably have to add something to the paper. Okay, so I can define functors C plus and I plus, which are some promotions of the old functor C and I. Namely, you're tensoring over H and tensoring over Z as before. However, I'm thinking of this as going from this category to that category. So from between the Fourier-Jacobi categories. And so in order to say, I have to explain how MP acts on C plus tau. Well, it acts just diagonally because tau was a representation of MP, and omega bar is a representation of MP as well. So then I'm taking the H coinvariance. And so the MP action is diagonal and it descends to SP. Because if you have a tensor product of two genuine representations of MP, then it descends to SP. So rather than say that it does not descend to SP, that's equivalent for irreducible representation, I should say that the pre-image of the identity acts by -1 or something. The second pre-image of the identity acts by -1. That's probably a better way to say it. And the tensor, it's not close. And you take tensor product, you get a representation of SP. So this guy is a representation of SP, and the Z action is simply through the action on tau, or equivalently on omega bar, because, okay, let's just say it's on tau. The Z action is on tau. Because we started out with some representation of, of H, which in particular was a representation of Z. And in the second case, on this I plus, I have an action of MP by the diagonal action of MP, and the H action is U. This should be omega. Yes, this is, is that the omega bar correct? But anyway, it doesn't matter. Putting the bars in the right place and so on. But okay, so I explained how to define these functors. And so you have to prove various things that, indeed you go from this category to that category and back. And the theorem D is that they are quasi-inverses. Thus, the category of genuine representations of the Fourier-Jacobi group is equivalent to the category of non-singular representations of SP times Z, SP cross Z. Okay, so that's all I have to say.
Okay, thank you very much. So any questions? See, I have one question. So this work works for infinite dimensional Heisenberg, right?
No, we only did finite dimensional. So we should, yeah, this is all finite dimensional.
Okay.
So it's a very good question to ask. What about infinite dimensional? So you see, you guys in the OA theory probably care about some infinite dimensional version of this result.
Exactly.
So therefore, it would be easy to prove such a theorem, since we already have some, I mean, we'll know that it's the right theorem.
Yeah. So you see
for Dima and me and for Raul, we were working with Whittaker functions, so all of our Heisenbergs are finite dimensional. And so we would probably, if we tried to just do it, we would prove the wrong theorem.
You see, the reason I'm very interested in the infinite dimensional case is because, see, first of all, Heisenberg, infinite dimensional Heisenberg gave us a vertex opera algebra.
Yes.
And a modules. Okay, modules for the vertex opera algebra.
Right.
And then you see the main thing, the reason I'm interested is this. You see if we wanted to use vertex opera algebra to construct conformal field theory in the sense of Siegel, the module for these vertex opera algebra are not really a complete topological space. So we actually have to find some topological completion. I did that. Okay, I did find topological completion, and Schweigert and a former student of him, they proved that my topological completion is actually nuclear.
Oh, good.
Yeah, so that's actually very nice, because if it's not nuclear, it's bad. You see, actually
if it's not nuclear, then it's unclear.
You cannot do much. And then see I think also Goddard has some kind of a topological completion. Actually, they prove that it's not nuclear. So anyway, the interesting thing is this: if this type of thing can be generalized to vertex opera algebra, then see a lot of things can be done. So, for example, it's a Heisenberg will be interesting certainly, because it's the simplest vertex opera algebra. Yes. But see, then one can ask the question for Versora and also for alpha Lie algebra, can we do the same thing? If we can do that, would be really nice.
The infinite Heisenberg one is a Borchardt-Kac-Moody. If you have one,
No, it's
Okay.
just
Maybe we can stop the recording. What do you think?
oh, okay, yes.
Actually, what maybe I can insert